Zohar for the first lecture in his series on beyond local operators. Please.
Thank you very much. Thanks for coming, everybody. Let me. So I'll start by just a general introduction, and I'll tell you what I'm going to explain during the course of my 3 lectures. And well, the TA sessions will be supplementary to what I'm going to explain. So the general background for these lectures is that from around the 1970s, in the 1970s or so, quantum field theory became sort of a well-established subject. Effective field theory was understood around that time. UV complete quantum field theories were discovered around that time. And the focus of research has been on local operators, which depend on time and space. These are some average values of some local observables. And people have studied very intensely correlation functions of various local operators. And we've learned about the concepts of gapped versus gapless. We've learned about the concepts of symmetry breaking and many other things due to the development of the theory of local operators. We've also learned about universality classes, about critical exponents, about conformal fixed points, about so many concepts over the last 50 years arose from a very intense theoretical and also experimental study of local operators in many body systems and quantum field theory. By contrast, and also I should say that for the mathematically oriented students here, in parallel there is also the whole framework of algebraic quantum field theory, which axiomatizes the whole concept of local operators, of the concept of locality, and it's all centered around local operators in many body quantum systems. By contrast, more recently, well, of course, there were some predecessors also in the past, but more recently, there's been a lot of interest in operators which are extended. So they're not local in space-time. And that's the word extended that I'm using in here. There is a lot of interest in extended operators. And there are several ways of thinking about extended operators. There is currently no axiomatic framework that explains how extended operators interact with each other, what are the general rules of extended operators. So it's more like we know a few things. I'll explain a few things. Some things are known better than others, but there is no analog of algebraic quantum field theory that accommodates extended operators yet. And there is a lot of interesting phenomenology, applications in many body systems, in quantum information, in quantum field theory of various extended operators. And so that's the main subject of my lectures, of what is there beyond local operators. Now, extended operators, you can ask what for? Why are we even interested in extended operators? So first of all, they're an integral part of quantum field theory, and also many body systems. If you want to really unravel that subject, these things have to be considered. So number one is that extended operators are really integral. They're that's reason number one. Reason number two, which is what I'm going to explain first, is that the concept of symmetries that you're very familiar with is basically an example of extended operators, including the notion of generalized symmetries. I'll talk about it today. Then, as far as also practically speaking, many body systems usually have impurities, and impurities are a special example of extended operators. So we have some practical applications, like for the physics of impurities. And also there are lots of other reasons, but for instance, the problem of confinement versus deconfinement cannot be easily probed with local operators, and we have to think about extended operators. So extended operators are also order parameters. They're order parameters for topological phases, for confined versus deconfined phases, and lots of things of that sort. So there are lots of applications for extended operators, and very little is known about them. And that's, yeah.
Wilson lines, for
Yeah,
example?
Wilson lines are like when I said order parameters for confinement versus deconfinement. So some of the first extended operators, namely Wilson lines, were invented by Wilson for that sake, to separate confined from deconfined phases. So, okay. But the thing goes much beyond that. For more recent developments like non-abelian topological phases, the order parameters are in many cases beyond Wilson lines. Okay, so this is the big picture, and what I'm going to do in these lectures is the first lecture will focus on extended operators, which are maybe of the most familiar kind. They correspond to generalized symmetries. And I'll also talk a little bit about anomalies in generalized symmetries, because I will need that for applications for some impurities at the last lecture, which are boson. Okay. In the second lecture, I'll focus on extended operators which are not associated to symmetries. They are not topological, just the general theory of what is the renormalization group flows on extended operators, etc. And in the third lecture, I'll focus on examples of applications associated to what's called in condensed matter the boson-Kondo problem, but it also has a very nice quantum field theory description. It's a pure quantum field theory problem that has various applications in condensed matter. And it's just a nice example because it would involve combinations of RG flows, some symmetries, some anomalies. So that's why I decided to present this example, because it's a nice application of all these ideas. Yeah, any questions about the outline or the motivation of why we need extended operators? Okay, one thing that I wanted to begin with is that if you think about when I say quantum field theory, I don't want to keep repeating that. I always mean many body systems or quantum field theory. I just don't want to keep repeating the same. So if you think about quantum field theory, let's say you have some space, X, it's in some RD -1, and you have time. When we have local operators are always at a given point in space and at a given point in time. So they just probe the physics at that time and that point. Extended operators could be extended either in time or in space. So let's say we have an operator which is supported on a line. So the line could be at equal time, or the line could be extended in time. And it could be a point in space, right? And in fact, if you believe in weak rotations, which are applicable in relativistic quantum field theories, there should be some correspondence between these two pictures. But these two pictures are physically very different. If you think about an extended operator at a given snapshot in time, that's just an ordinary operator acting on the Hilbert space. So when it's the word extended operator is best applied when it's when the operator is at a given time, and it just acts on the Hilbert space. Okay. If you think about extended operators where one of their directions is extended in the time direction, maybe the word extended operator is not very appropriate. We might call it an impurity or a defect. So when it's extended in the time direction, it's better to refer to these objects as defects or impurities, because they describe deformations of the Hamiltonian. So this is the Hilbert space. If the same operator, you just weak rotate it, and you extend it in the time direction, you can think about it as a defect or impurity, and so you should think about it as a modification of the Hamiltonian by a defect Hamiltonian. You might also need to modify the Hilbert space. So it might be that this total Hamiltonian, including the defect, acts on a slightly extended Hilbert space from the original Hamiltonian. So it could be that there is a new qubit associated with the impurity, or a new set of degrees of freedom associated to the impurity. So even the Hilbert space on which this acts might be slightly larger than the original Hilbert space. Yes, Frank?
Are you assuming that the original Hilbert is translation invariant?
Let's assume that we're dealing with just quantum field theory with Lorentz symmetry, or many-body systems which are translation invariant in time and space. Yeah. So these two perspectives, they're wildly different if you think about lattice models. What is the connection between acting on a given Hilbert space of lattice degrees of freedom versus modifying the Hamiltonian and studying some defect Hilbert space? There is no connection.
Is it like a quench? You're thinking about a quench?
That would be a quench. The first one is not a quench. The first one is just you act.
I don't understand what it is.
I'll explain. Maybe I'll try to explain again. So these two perspectives, they are very different in many-body systems, but in Lorentz invariant quantum field theories, they should be related, closely related, because we can always choose how to quantize the theory, whether this is time or space. So this perspective, where it's extended in time, it's like you've added a defect that has been in the system forever and ever, from minus infinity in the past to plus infinity in the future, and you have a time translation invariant Hamiltonian that includes a defect. It's like you have a piece of metal that has always had a piece of garbage at some point x equals 0, and that's it. And it interacts in some way with the ambient electrons. Okay, so that perspective doesn't have a quench. Also, that perspective is nothing to do with a quench. That's just when you take a state in the Hilbert space and you act on it with a space-like operator, which happens to be extended. You could take a product of spins at various points and just act on the wave function.
Would that be the defect?
That's what an extended operator does. So that's why I'm using the terminology extended operator. Instead of acting on the wave function like at one point, you act on the wave function by a very non-local operator. So you could call it a non-local operator or extended operator.
That's a quench.
No. A quench is when you have a defect that is extended in the time direction, but it has an endpoint at some point t equals 0. So before time equals 0, there was no defect, and after time equals 0, there is a defect in the Hamiltonian, and that's a time-dependent Hamiltonian now. Okay, so you put an extended operator, but with an endpoint. That's what people call a quench. A quench. That's what people call a local quench. Okay. I'm actually not going to discuss local quenches in these lectures. Okay, so this is the big picture introduction, and I'm going to discuss first a very special class of extended operators or defects or impurities. I have to go between these three words which are basically synonymous, which are associated to symmetries, and that's the subject of generalized symmetries. Yes?
So I think what Yannis asks is, if you have codimension 1 extended defect, it is a quench in general, because you can change the Hamiltonian.
A quench is, well, it's a matter of terminology. A quench...
An interface, a Euclidean interface is a quench.
So it's a matter of terminology. What people call a quench in condensed matter is that you change the Hamiltonian and t equals 0. For that, you need an extended operator that is extended in time after t equals 0. Extended after, so it exists after t equals 0. It does not exist before t equals to 0.
It's semantics.
It's semantics, yeah, but that's what people actually use it as a, that's how, the way I'm saying it is how people use that word. When you have this situation, that there is a defect at any moment in time, in the past or in the future, that's what people call a defect Hilbert space. That's this description, and it's not a quench. Okay, any general questions about the outline? Okay, so the first, so today I'll discuss extended operators of a familiar kind associated to symmetries, starting from netter symmetries, and then going to generalized symmetries and some anomalies. Perhaps before I go there, I just wanted to make one more general comment. When you learn about local operators, you learn about this mysterious thing that's called renormalization. So one of the mysterious things, or one of the things you learn, is that when you try to make sense quantum mechanically of some operator, you might need to multiply it by a constant, which is a wave function renormalization, if you've heard these words. And so the normalization of local operators is a little bit ambiguous. It's a little bit a change. There is a question of scheme, etc., etc. One thing that is fantastic and very interesting for extended operators is that their normalization is unambiguous. So if you have an extended operator, let's call it E. Let's say it's a codimension P operator. So it's let me just draw a picture. Let's say we have two-dimensional space, two-dimensional space-time, and we have an operator which is a line operator. So let's call it E. The normalization of E is completely unambiguous. You cannot multiply E by square root of 2. That's just an illegal operation in the space of possible operations on extended operators. Does anybody see why that's illegal? Why?
There's no open space.
Yeah, it's because we've said that inserting the operator like that should lead to a Hilbert space interpretation with some piece of garbage that's present in the system. And if we just multiply it by square root of 2, it wouldn't make sense to assign a Hilbert space interpretation to it because the number of states would not be an integer. So partition functions in the presence of extended operators have to count states. So the normalization of extended operators is unambiguous. That will be extremely important in the lecture tomorrow, especially. Yeah.
But you could multiply it by E2 length times.
Right. So you can ask, can I multiply it by an exponential of the integral over the world line, let's say, with some coefficient alpha? Yes, that is legal. That's a legal thing to do. And the interpretation of that in the Hamiltonian language is that you've just changed what you mean by the 0-point energy in the defect Hilbert space. Because you are integrating over the world line of this extended operator. So you've just changed the 0-point energy. So you cannot multiply them by a constant, but you can multiply them by something that is integrated over their space-time of the extended operators. And this will be very important in the lecture tomorrow, that their normalization is unambiguous up to local terms. Okay? So and another thing you could do, I'll get back to it, is to multiply by them by 2. You can multiply by 2. That also makes sense. But I'll get to it a little bit later today. You cannot multiply them by square root of 2, but you can multiply them by 2. So extended operators have their own rules, and I'm going to try to explain some of it to you. Okay, so the first example, as I said, of extended operators that we'll see are associated to symmetries. Just classical symmetry is something that you've seen in basic graduate courses. So maybe this is the most famous construction of an extended operator. Suppose we have a system with a conserved current, J mu. Then let's go to Euclidean signature, just so that we don't have to keep asking if it's in the time direction, is it a defect, or is it in space, just an extended operator. So let's just go to Euclidean signature, so that everything is uniform. So a very famous construction of an extended operator that lives on a space of dimension d minus 1. Let D be. Let the space be R D. So D is now the number of space-time dimensions in Euclidean signature. So an operator that lives on a subspace of dimension d minus 1 is obtained by exponentiating the current, the integral over the current. So it's an integral over sigma d minus 1 of star j. So j is a 1 form, which is conserved. Then star j is a d minus 1 form, which is closed. And we can integrate it over d minus 1 dimensional manifold with coefficient alpha. And we get an operator. Let's draw this operator. We get some operator. Let's say in 3, this is R3, and this is sigma 2. Sigma 2 is some two-dimensional space, and we've integrated star j on this two-dimensional space. And so this operator depends on the space, but okay, I'll explain some properties of it now. Are there any questions about this construction? Yes?
Does it assume U1 symmetry if you just have alpha?
Yeah, there could be many currents, so there could be some index A here, and I could put alpha A, J A. I'm just going to suppress these indices for now. Any other questions? Okay, so the main property of this operator, that is the claim to fame of the Netter theorem, of course, is that you could change the space on which you integrate these operators smoothly, and it doesn't really affect the operator in the sense that it doesn't affect how it acts on the Hilbert space in Minkowski space-time, or it doesn't affect which exact piece of garbage or impurity it leads to when you extend it in the time direction. So it's a topological operator. It's a topological operator because star j is a closed form. It's a topological operator of codimension 1. Okay. So what does this operator do? If you just insert this extended operator into correlation functions, and there is nothing inside, and this is just a 2-cycle that can be collapsed, then it doesn't give anything, it's just 1. But more generally, there could be an operator inside, O of x. And because this surface is topological, you can just shrink the surface around the local operators, and that would give a new local operator, O prime of x. And we interpret it as the action of the associated symmetry on the operator. And we can also write it as U O U minus 1. It's the same as surrounding the operator by a dimension 2 surface and collapsing it because of the following. So if this is U and this is U minus 1, so this could point here, this could point here, you can just continuously deform it to a closed surface around the operator. So I'm just saying the usual action of symmetries, which involves acting with the unitary slightly before the operator, and then comparing it to what happens when you act slightly after, is the same as integrating the operator in some closed manifold encompassing the local operator. And that's how you get a new local operator, which we interpret to be the symmetry transform operator, where the symmetry is associated to this current J. Okay, so that's just the usual Netter's theorem explained in maybe a slightly more modern point of view. Are there any questions about it? This is so if there is anything that's unclear about it, just stop me. It's okay, very good. So another thing we can do with this operator U is that we can try to surround a local operator by 2 of them. Maybe this is associated to some alpha, so I can put an index alpha here. So now I can just surround it by 2 integrals. Let's say this is U alpha, and this is some U beta, and this is sigma 2, and this is sigma 2 prime, which is this surface. And you can ask, what is it going to do to the local operator when I squeeze it inside 2 surfaces? So that's like acting on the operator with the first symmetry, and then acting on the resulting operator with the second symmetry. And that's the same as composing the 2 symmetries, essentially. So we can say that U beta and then U alpha is the same as U beta composed with alpha, where the composition is like, in the case of Netter symmetries, this is just group composition. So beta and alpha are some elements of a group, and well, e to the I alpha and e to the I beta are elements of a group, and that's the same as the group law. Or maybe written more conventionally, UG prime is the same as UG G prime.
Currents have to be the same. Yeah? The currents for the two U's have to be the same.
Well, not necessarily, no. So it works for any two group elements. So in Nether's theorem, well, we can have any symmetry with group element G. It's associated to a topological extended operator of codimension 1. We can compose two of them, and we get U that corresponds to the composed elements. So they don't have to be the same. Any two symmetries work. Okay, so these kind of constructions are the simplest extended operators. They're associated to symmetries. And furthermore, in Nether's construction, the possible things that you can obtain correspond to a group, because for every topological operator U, there's another topological operator U minus 1, which is associated to the group element G minus 1. So the topological surface associated to the element G, if you try to invert it, it's the same as the topological surface corresponding to the inverse element G of G. And that acts as an that acts as an inverse in the sense that if you try to compose two of them, you get the unit operator. So these are just the standard properties of symmetries in quantum field theory. Any questions about it? Okay. Now, you can ask a deep question to which the answer is not known. Are there topological codimension 1 operators that do not correspond to Nether charges or to group elements? So you can ask, are there codimension 1 topological extended operators? So let me just write topological operators. Not of this type. By this, I mean that they correspond to some symmetry of the Hamiltonian, a symmetry of the Nutter type, corresponding to some group G. Okay? Or G is some element in a group G. So the answer to that question is no. The answer is yes. We by now have many examples of many-body systems and quantum field theories with topological operators not associated to any known conservation law. So there is no transformation of the Hamiltonian of the ordinary Nutter type that corresponds to these operators. We don't know how to find them systematically. So once in a while there is a paper on the archive saying, oh, look, this theory has this topological extended operator that we didn't know about. We don't have a systematic way to find them, but they certainly exist for non-group. They certainly exist beyond Nether's theorem. So these are maybe called generalized symmetries.
What do you mean by systematic? Like, in what sense is it more systematic to find the conventional symmetry?
Well, for Nether charges, we have a systematic way of finding them, which is that you write the equations of motion, and you ask what is the space of transformations on the solutions, which take solutions to solutions. And the transformations have to be group-like. So every transformation has an inverse. So, I mean, it sometimes so happens that some differential equations have more symmetries than what you knew about, but it's a very systematic procedure, in my opinion. Here, we don't have any idea of how to look for them, even remotely. So whenever you find a new topological operator in a system that wasn't known before, it's well worth a paper, typically. Okay? So you just stumble on, you can prove that they exist with some ad hoc tricks sometimes. You can stumble on them accidentally. Yes?
Also clearly say that many bodies, actual systems of that, you say establishment there.
They're the same, what do you mean by same
You also
thing?
say that there's no systematic classification or no idea how to classify.
Oh, just in the recent 5 years, there were probably over 100 papers with new conservation laws in very simple lattice models that were known for decades. Yes, so I would say it's not, we don't know how to look for them very efficiently, at the very least.
Yeah, I would say that at least in one there is some partial classification.
Yeah, there is a classification of what they could look like, but given a system on the lattice, I'm not sure it's very easy to determine which actual generalized symmetries it admits. I would say this is true. We do know that generalized symmetries are not super wild. They have to obey some axioms from category theory or fusion code. But it doesn't mean that you can easily find them when I assign a given system to you.
No, I would agree with that.
Okay, good. So we're in agreement. Any other questions? So the subject of generalized symmetries begins from here, looking for extended operators which are topological and are not of the nutter type. That's the beginning of the subject. Another possible notion of generalized symmetries is you could ask, why are we even interested in topological operators which are codimension 1? What's so special about codimension 1? Maybe there are topological operators which are codimension 2 or codimension 3. And these are also possible indeed. So the subject of higher symmetries, the subject of higher symmetries is essentially about topological operators which are not codimension 1. So the terminology is that if you have a topological extended operator of codimension p plus 1, we say that the system admits a p-form symmetry. The system admits a p-form symmetry. I'll give some examples in a second. Okay, so this is the definition. And some interesting many-body systems and quantum field theories admit p-form symmetries associated to. These are very much beyond Nether, because in Nether's theorem, it's not even clear how would you get something that's not codimension 1. Okay. Now, what are the properties of p-form symmetries? I'll just explain the basics. It will be somewhat important for later lectures. So, codimension 1 operators act on local operators. So you can say that local operators are in representations of the symmetry. Codimension p plus 1 operators, they cannot act on a local operator. So imagine we're in 3 Euclidean dimensions, and you happen to discover some codimension 2 conservation law. So some operator, which is the line operator, which is topological. There is no way in which the line operator can act on a point. You cannot surround a point by a line, because if the line is truly topological, you can always move it outside of the point, away from the point. But a line operator can act on a line by linking, for instance. By linking. So this is a topological line, and this is a general line that doesn't have to be topological. So one-form symmetries in 3 dimensions, in 3 space-time dimensions, would be topological lines, and they could act on line operators via linking. They can also act on surfaces. So you could also ask what happens when a topological line acts on a surface. That also makes sense. And in general, p-form symmetries act on objects of dimension q, where q is not smaller than p. That's a general property of extended operators, extended topological operators, that they can act on various other extended operators. Okay, So now I'll go to an example. What's this? Yes?
How should I visualize how the line operators that can potential what on surfaces?
Yes, so the question is how do we...
How does that actually?
oh, I wrote the, I wrote the inequality incorrectly, of course. I wrote it incorrectly. So it's Q smaller than P. But not always non-trivially, so what I meant is that a surface, let's suppose you have a topological surface. A topological surface can act on a line inside to produce a new line.
Maybe like the inequality is the other way around.
Yeah, but maybe with codimension, yeah. So a topological surface can act on a line. A topological surface can act on a point. So I think I should use the word codimension to make it precise. And then this will be the correct inequality.
I see. I think earlier you said the line.
Yeah, I said it the wrong way. A surface, a topological surface, can act on a line to produce a new line. A line can act on a line to produce a new line as well, like in this picture. So a line can act on a new line to produce a new line, and a surface can act on a line to produce a new line. A surface can also act on a point to produce a new point. So the correct inequality is like that, but with codimensions. Okay? So the world of extended operators has all this zoology, and now I just wanted to give you an example so that it's not super abstract. I'll give one example of one-form symmetry. Sometimes P-form symmetries are group-like. They correspond to an abelian group, but they don't have to. By now we have examples where they don't correspond to a group. So I'll just write it here, and then I'll give an example. Sometimes P-form symmetries correspond to a group. So what do I mean by that? Imagine there is a line operator, which is not topological, and we act on it with some topological one-form symmetry in R3. We might produce a new line, L prime. Then we can encircle it by another one, and we can discuss the composition law. We can discuss the composition of what happens when you encircle a given line by two topological operators of codimension 2. So they could act as a group, meaning that you could first shrink the first, then shrink the second, and you could get a group. That group has to be abelian. Does anybody see why? Does it have to be abelian? Because you can always change the order in which you shrink the loops around an extended around the line operator. So that's why it could be a group which is abelian. Cannot be a non-abelian group. If it's a group, it's abelian. But it doesn't have to be a group. We also have examples where these topological codimension 2 operators do not correspond to group elements, and it acts in some categorical way. So it could be.
Surfaces, that argument wouldn't apply, right?
Right. For surfaces, these are the Noether symmetries, and Noether symmetries don't have to be abelian because the order matters. The order of the fusion matters. I'm saying that for P-form symmetries, so in the world of generalized symmetries, there are various extensions of the ordinary notion of symmetries. Ordinary symmetries are non-abelian, codimension 1, topological surfaces, corresponding to a group. And these words can be extended in various ways once you just accept the topological operators are tantamount to symmetries. So one extension is codimension 1, but does not correspond to a group. This whole story of fusion categories is part of that. Another way is that maybe it's not codimension 1. Maybe it's codimension 2, and it corresponds to an abelian group. Or it could be codimension 2, not even corresponding to an abelian group, but something else. So there are various extensions. So sometimes p-form symmetries correspond to an abelian group, and sometimes not.
So sorry, in this statement, when you say p-form symmetry, p is bigger than 0?
No.
When you said that
P-form symmetry is just a codimension p+1 topological operator.
Right, so if p equals 0,
That's ordinary nether symmetries,
So-
if they correspond to a group.
I understand, but you said it has to be a abelian group, so that's only for p.
Yes, you got me. Are you a mathematician?
I'm afraid so.
Sorry. Yeah. Okay. So for p bigger than 0, it has to be an abelian group if it's a group. If it's not a group, then it's not a group. It's some other structure. Okay. Any other comments? Okay. So an example. I'll give one example, which is just let's consider Maxwell theory in d dimensions. Let's do d space-time dimensions. F mu squared. So in this theory, there is an identity, which is Bianchi's identity. And because of the Bianchi identity, we can consider an interesting operator, which is an integral on the surface. So we can take the tool surface and exponentiate an integral over the field strength. Okay? In 4 dimensions, if d is 4, that is a one-form symmetry, because it's on a codimension 2 surface. In 4 dimensions, that's a one-form symmetry, which corresponds to the abelian group U1. In 3 dimensions, that's an ordinary zero-form symmetry. Okay, so this is a universal thing that exists in Maxwell theory. It's called the magnetic U1 symmetry in the literature. Now you can have an interesting discussion. What does this symmetry do when you think about it as an operator acting on the Hilbert space of Maxwell theory? Or you can try to orient one of the directions in the time direction and think about what is this impurity doing? What is the physics of this impurity? What does it describe? Okay. You can also ask what is it acting on? If it's a symmetry, it should act on line operators. Which line operators is the symmetry acting on? So it's a one-form symmetry in 3 + 1 dimensions. Therefore, there must be some line operators on which it acts. And it turns out that these are the 't Hooft lines. So the 't Hooft lines that you might have heard about in Maxwell theory are charged under the magnetic one-form symmetry. They're acted upon by the magnetic one-form symmetry. Okay? Okay, so this was just a quick introduction to the zoology of symmetries and topological operators. Just to put the discussion of extended operators in a little bit of context. Now I'll get to something a little more concrete about the operations that we can do on extended operators, and then anomalies of symmetries.
Sorry, this example, is it the same for non-abelian gauge theories, essentially?
So the question is whether there is a magnetic one-form symmetry for non-abelian gauge theories. The answer is yes, but it's discrete, not continuous, and it depends on what's the gauge group, very sensitively. Okay? There is no Bianchi identity for non-abelian connections. There is a non-abelian generalization of the Bianchi identity. and so you cannot literally integrate the field strengths. That doesn't make sense. But there is a discrete version for some gauge groups. So for instance, for SO3 gauge theory, there is a Z2 one-form symmetry, which is magnetic. There is a Z2 magnetic one-form symmetry. Okay? Yes?
So you mentioned that when we have this P-form symmetry, there is an extended object that's coupled under the field.
Yes.
But if you have an extended object in your field, is it guaranteed that you have also high-form symmetry?
No. Many systems have extended operators and no corresponding symmetry that acts on them. It's in the same way that many systems have local operators, but no symmetry that acts on them. Yeah, so typically a system has lots of extended operators, which are not topological, and no topological operators that act on them. Topological operators are like symmetries, so they're more special. Okay?
Oh, sorry, just to make sure I'm not getting confused. If I have a non-abelian gauge theory, the curvature is still closed, right?
No, but you not with the differential D. That's not true. What's true, you have to use a different differential. You have to use a covariant differential, and also F is not gauge invariant. So you cannot literally use this expression.
But you could take, for example, trace of F and integrate.
Trace of F is vanishing for semi-simple Lie groups.
It's true.
So it's not so easy. So people have spent some time trying to generalize this construction for non-abelian gauge fields, and there is an analog, but it's not trivial, and I'm not going to explain it in these lectures. I'm just going to tell you, for instance, that for SO3 Young-Mills theory, there is a Z2 topological operator of codimension 2. That's a fact that we know. Okay. For Maxwell theory, you can just write everything explicitly. For non-abelian gauge fields, it's much more difficult to write explicit formulas. Okay? Okay, so now I just wanted 5 minutes on the operations. When you have topological operators of codimension P, let's say you have two codimension P+1 operators. They don't have to be topological for now. Okay, any codimension P+1 operators, they don't have to be topological or anything special. The question is, what are the operations that are allowed? So, why am I discussing operations? When you have local operators, what can we do with local operators? Can somebody, let's say we have two local operators, O and O prime. What can we do with local operators? Differentiate. So one thing is we can OP, right? We can replace them by an infinite sum of effective local operators. We can do OP. We can also add them. Does that operation make sense for local operators? Yes. The question is, what are the analogs of extended operators? Can we add them? Does it make any sense to take two extended operators and add them? Let's say they live on different sub-manifolds. Does it make sense? No. No? Doesn't make sense, right? What does it even mean to add extended operators? Yes?
You evaluate correlator with one and add correlator of other.
So you can do this, direct sum. So this makes sense. A normal addition doesn't make sense, but a direct addition makes sense. And the meaning of that is that, as Ingo said, one practical thing that this could mean for you is that in every correlation function, you would just take the sum of the answers. You evaluate it with one, you evaluate it with the other, and you take a sum. This is called the direct sum. This is called the direct sum. And if you think about them as defects, if they're extended in the time direction, that means that the Hilbert space of defect number 1 is a direct sum with the Hilbert space of defect number 2. Okay, so it's like you have a system with an impurity, but the impurity didn't decide if it's in location 1 or if it's in location 2. So you have to take a direct sum of the two Hilbert spaces. It's a slightly unphysical procedure. How do you cook up in an experiment an impurity that forces you to take a direct sum? So you have to imagine that maybe the impurity has some kind of potential, and there are two minima, which are extremely deep, and the impurity is either in this state or in that state, and these are like two superselection sectors. So it's what you might call superselection. Okay. This direct sum operation that we can do with defects, extended operators, is maybe slightly unphysical because it requires impurities to have superselection sectors. But it happens in many, many examples. That this is the infrared limit of some non-trivial defect, or that's an effective description of some defect, etc. So this operation is difficult to understand. Yes?
So isn't this a quantum dot, which can have many states?
Yeah, but typically it's not a direct sum. In a quantum dot, the states...
The electron is here, spin up, one defect,
So-
or it's spin down.
Yeah, but usually they are coupled to each other. This operation arises only if the defect has two states. It's not a superposition. In quantum mechanics, we have this is not superposition. That means that either the system is in that Hilbert space or in that Hilbert space. It's like the defect has two superselection sectors. This appears though in many, many applications in impurities. So it's an important operation. So that's one operation we can do, a direct sum. And sometimes when people, that's why you can multiply a defect by 2. When I told you that you can multiply a defect by 2, what I really meant is that you can do a direct sum of the defect with itself. Okay? Yes?
When you pass the defect over space, you have a localized Hamiltonian perturbation at that defect, right?
Yes,
If
exactly.
you have two defects in this direct sum, can you have a Hamiltonian that couples these two?
No, that's exactly the point. So this direct sum is like saying that the defect is in one of two states, and there is no coupling between the two states. It's like the Hamiltonian splits to a matrix, which is a block diagonal matrix. So this just means that the full Hamiltonian of the defect is block diagonal, with one block corresponding to defect 1 and one block corresponding to defect 2. So it's like the tunneling is suppressed to 0. Or that's why I said that there is a potential barrier, which is infinite. It's something that's almost never exact, but it's the correct infrared limit of many defects. Because in the infrared, the potential could look infinite, right? When you do a renormalization group scaling argument. Okay, yes?
Why did you draw a distinction between adding local operators and direct sum?
Say again?
Why did you draw a distinction between adding two local operators and this direct sum of the defect?
This is an addition. Well, why did I draw a distinction?
Without correlators back to two, right?
You might say that the direct sum is a generalization of the ordinary arithmetic sum. I think it's a matter of semantics. I just wanted to emphasize that you have to make sure that you understand what addition means in the world of extended operators. Addition means that you make the full Hamiltonian block diagonal in the defect interpretation, and there are two blocks that don't communicate. Okay? So that's why it's called the direct sum. So that's the analog of addition. We also have an analog of OPE. So let's say we have two surface operators. We could put them next to each other in parallel and try to interpret this configuration where there are two impurities as a fused impurity. So it's like a fused impurity. So you can develop a notion of an operator product expansion for defects when you put two defects at the same time. So these are two impurities at different locations, and you try to interpret it as a composite impurity. So you could try to interpret it as a sum of some effective surfaces. So we have an operator product expansion for parallel defects. You can ask, what if they're not parallel? Then I think we basically don't know the rules of the game yet. There are no papers about it, really, that discuss what's going to happen in that case if the defects are not parallel. But for parallel defects, we have examples where this can be shown to hold. Okay? So we have a notion of parallel fusion. We have a notion of direct sum. And this is just the general structure. Oh, by the way, maybe one answer to your question of why did I draw a distinction between sum and direct sum. In a sum, you can put any coefficients, alpha 1 and alpha 2. In direct sum, the only coefficients are positive integers, or 0, so no negative integers. You cannot put arbitrary coefficients, it doesn't make sense for the interpretation in Hilbert space. Okay? And that's also why I said at the beginning that the normalization of defects is well defined. There is no multiplicative renormalization. Their normalization is universal. Okay, yes.
How do you fix the normalization when the defect Hilbert space is empty?
If the defect Hilbert space is empty, then the normalization is ambiguous. I agree with that. That goes into, I mean, then you have to fix some fractionalization classes probably, like you did in your paper, and you're just, you know the answer better than me.
Your paper.
Yes. Any other questions?
All these operations are for generic, non-topological.
Yeah, so we know that these operations make sense for generic defects, non-topological ones. It's hard to understand what happens if they're not parallel, what is the correct language. For topological defects, we know more or less what to do. That's where anomalies enter, and that's what I wanted to explain now. Anomalies come from configurations of topological surfaces which are not parallel to each other. Okay? So I'm gonna explain it now. Yeah.
So you said only parallel defects can have OPs, so you mean?
No, I didn't say that. I said we don't know how to do it otherwise yet.
Ah, okay.
It makes sense if you think about it as a quantum any-body system, because if you orient it in the time direction, it's some impurity. It's a piece of garbage that's like lying at some point or maybe along some line. So if you have two pieces of garbage in parallel, you can replace it to effective garbage in the same shape. But if the garbage is not in the same shape, it's hard to understand how to replace it by something effective. Okay? So, okay, now anomalies. That would also be important for. Okay, so far we discussed. I'm going back to Nutter symmetries. I'm going back to Nutter symmetries. And I'm even going all the way to quantum mechanics, just for the sake of simplicity. That's all I'll need for this course. I'm not going to try to teach anomalies beyond quantum mechanics. I won't need that for this course. So we're just going to discuss ordinary Nutter symmetries in quantum mechanics. So quantum mechanics is something that's happening at, on the world line, and time is running upwards. And conserved charges correspond to unitaries, U alpha, U beta, and they're time independent. So that's what the conserved charge is in quantum mechanics. It's some unitary that's time independent, commutes with the Hamiltonian. And that's the extent to which it's topological. You can just move it around with no price whatsoever. And now, when we discussed the group law, I told you that if you take two unitaries, they compose like the group multiplication. And here there was a small line, and that's the root of anomalies in quantum mechanics. In quantum mechanics, it's possible that while the classical symmetry is some group G, when you compose the symmetries as quantum operators, there is an additional phase, let's call it epsilon, which is a function of alpha and beta. So anomalies are just pure phases, which violate the multiplication law that is classically true. So we have some classical multiplication law associated with a group, but quantum mechanically, when these are realized as operators, there is an additional phase. Now, does this phase matter? When you act on local operators, remember that in quantum mechanics, the way we act on local operators is from acting from below and acting from above. So if we wanted to act on some local operator, we will have the inverse here. And so this phase would cancel out. Can everybody see that the phase cancels out when we act on local operators? It's because we act from below, we act from above, So if there is a phase, the phase cancels when we fuse these operators versus when we fuse these operators. Is that clear? Good. So these phases don't matter as far as the action on local operator goes because they cancel out. But if you act on wave functions, they matter because wave functions in quantum mechanics correspond to running the path integral from some time t equals t0. That's a wave function in quantum mechanics. And then we act on the wave function with the operators u, but we don't have operators before. So wave functions are acted by u, but operators are acted by u times u inverse. So therefore, this is very important when acting on wave functions, but not when acting on local operators. So that's why the classical and quantum symmetries could differ slightly. Classically, this goes away because the local operators and the phase space don't see it. But the wave functions see this space. Okay? I'll just summarize what I just said. Anomalies in quantum mechanics occur when topological operators anomalies in quantum mechanics occur when topological operators, namely conservation laws, topological operators are the same as conservation laws, fuse with a non-trivial phase. Okay. That's how anomalies in quantum mechanics occur. And I'll show you some examples why it's important and what does it give, what does it buy. So therefore, wave functions don't necessarily transform under the symmetry G, which is our original symmetry. So let's suppose the original symmetry is G, in the sense that G acts on local operators, and the phase cancels out. So wave functions don't necessarily transform under the symmetry G, but they transform under some extended symmetry that includes these phases. And so sometimes we say that wave functions are in a projective representation. So technically we say that wave functions are in projective representations. Okay, so local operators are in standard representations of the symmetry G, but wave functions are in a projective representation of the symmetry G, and that's when we say that a quantum mechanics model has an anomaly. And these anomalies are crucial for the following reason. These anomalies are crucial because sometimes projective representations cannot be one-dimensional. I'll show you an example in a couple of minutes of a system that has a quantum mechanical anomaly. And because the wave functions transform under G hat, the wave functions cannot be non-degenerate. And that leads to some theorems about, that, let's say, quantum mechanical systems with some interactions need to have more than one ground state. So you can prove very powerful results with just computing some projective phases. Okay. In higher dimensions, anomalies are also some deviations from the group laws. I told you that when we fuse operators, we just use the group laws. In higher dimensions, anomalies are much more difficult to describe. They have to do with topological operators that are not parallel to each other, and they have some funny phases. And it's well beyond the scope of this course. And that's why I'm just going to teach this example in quantum mechanics. That's what I'll need for the examples at the end of this course. Okay. But yeah, one thing to remember is that anomalies have to do with fusion of topological extended operators. Okay, now I'll show you an example. Suppose we have a system with Z2 times Z2 symmetry. I'll actually exhibit a system like that in a couple of minutes, but now I'll just develop the mathematics. So Z2 times Z2 symmetry means we have 4 elements, 1, A, B, and AB. A squared is 1, B squared is 1, AB is BA. This is the standard description of the client formula of Z2 times Z2. And while all these relations could be true on local operators, in some quantum mechanical systems with Z2 times Z2 symmetry, the operator A and the operator B and the operator AB are realized on wave functions in a slightly kooky way. So A could be realized as 1 minus 1, B could be realized as 1, 1, and AB would be realized as a 1, 0, and then minus 1, 0. Okay, so we will encounter an example like that in a moment. And of course, these matrices don't literally satisfy the Z2 times Z2 symmetries, so it's an illegal representation, but it's a projective representation. Because AB is minus 1, B squared is 1, AB squared is minus 1. AB squared is minus 1. And AB is not BA, it's actually minus BA. So you see? So if you think about these matrices as a representation of Z2 times Z2, that doesn't make sense. It's not a representation. But it's called the projective representation, because all the group laws that you expect from classical group theory are obeyed up to a few phases. Okay, so that's called a projective representation. And I'll show you how this comes about in a quantum mechanical model, where it can be interpreted as an anomaly, and it leads to very non-trivial consequences. Any questions about the group theory calculation? Now I'll show you an example. A squared is minus 1, that's what I... Oh, sorry, of course, yes. This is plus 1, sorry, I was doing it in my head. And AB squared is negative 1. Thank you. Okay, so now an example. I'll finally get to some physics. I've spent an hour telling you about the terminology. Now we'll do some physics with the Hamiltonian and so on. So I'll show you an example that will appear again in the last lecture. There will be an Aharonov-Bohm solenoid and a particle moving on a ring around the solenoid. And the solenoid carries flux phi, which is defined mod 2 pi. Just a standard solenoid. And according to Dirac's old story, we know that when the flux is 0 mod 2 pi, the solenoid is invisible. And then the particle is moving on a ring around the solenoid. What classically a particle moving on a ring is not a big mystery. The energy is just the frequency squared of the particle, and that's it. But quantum mechanically, the solenoid makes an appearance, and the Hamiltonian contains the solenoid flux explicitly. Let's say the coordinate along the ring is x, and let's say that x is identified with x plus 2 pi. And then the conjugate momentum is minus I d by dx. Okay, so let's solve this system quickly. That's the energy levels. Well, the eigenfunctions psi n are e to the I nx, where n is an integer. The energy levels associated to these eigenfunctions are 1 by 2m n plus phi by 2 pi squared. I have to put a 2 pi here. Okay, and the fact that phi is defined modulo 2 pi is very clear in the spectrum of the system. If you shift phi by 2 pi, the whole spectrum as a collection of eigenstates remains invariant, though individual eigenstates may change if you adiabatically change phi. That's closely connected to what's called a Thouless pump. But okay, the spectrum of energies is invariant under changing phi to phi by any integer times 2 pi. Okay, and now this system has two. What are the symmetries? Can anybody say what are the symmetries of a particle in a ring? Raise your hand. If you, what are the classical obvious symmetries of this Hamiltonian? Anybody has any suggestion? Yes, you're doing the right.
Translation in X.
Yeah. So what's the generator of that? What's the unitary? What's the unitary that generates translations in X? E to the I alpha P, I would say. And then alpha is defined to be up to 2 pi. Yes? This is the unitary that generates the translations. If phi is equal to 0, there is another symmetry, which is you can just flip the circle x going to minus x. That's also a symmetry. So for phi equals 0, meaning no Aharonov-Bohm solenoid, we also have the symmetry x going to minus x. It's generated by a quantum operator C, which acts on any function of x by flipping the coordinate. This acts on any function of x by shifting the coordinate x by alpha. There is another symmetry at phi equals 0, which acts on any function of x by flipping the coordinate x to minus x mod 2 pi. These two together, they form a group, which is, what is the, C, what's the algebra of C and U? If we do a rotation and then flip, it's the same as flipping with the opposite angle and then, sorry, it's the same as flipping and then doing a rotation with the opposite angle. And that group is known as O2. That's just how it acts on these functions of x. So there is an O2 symmetry when there is no flux. And how does it act on the wave functions? Well, at phi equals 0, the ground state is unique. At phi equals 0, the ground state is given by n equals to 0. And this C acts on the ground state by taking it to itself. And U alpha acts on the ground state by taking it to itself.
Sorry, this dumb question. What do you mean by ground state? Your n is any integer.
Yeah, but the ground state is the state with the smallest possible energy. Let's say when phi vanishes, that's the state is 0. So on the ground state, these symmetries. Okay. So this is just the story of a particle on a ring without flux, and the flux shifts the energies like that. There is another very interesting point, which is phi, when phi is equal to exactly phi. And that's the focus of what I'm going to explain now. Let's investigate now phi equals pi. That's when there is a half unit of flux inside the ring. What happens to that symmetry? That's intact. What happens to that symmetry? That's also intact. So there is a flipping symmetry also at phi equals pi, because if we flip the ring, the flux phi goes to x goes to minus x, therefore p goes to minus p, but phi is defined mod 2 pi, so you can compensate for p going to minus p by pi going to minus pi. And when pi goes to minus pi, it doesn't really matter, because phi is defined mod 2 pi. Is that clear, or it was a little too quick? You see that pi is an invariant point under changing the sign of phi, because pi and minus pi differ by 2 pi. Okay, but now, what about the ground state? Let's consider the ground state of this system. Now we see that the energy of the state 0 is the same as the energy of the state minus 1. Because when you shift this, because of the shift by phi by 2 pi, n is shifted by pi, n is shifted by a half, so n equals 0 and n equals minus 1 and give the exact same energy eigenstate. The exact same energy, I meant. Okay? And so we have a two-dimensional Hilbert space as the ground state in this quantum mechanical model. And the two wave functions are psi0 and psi1, and psi minus 1. So we have to realize our symmetries on these two ground states. And lo and behold, U alpha acts as 1, because this is translationally invariant. This is e to the minus I alpha. And C acts as 1, 1. Because, as I said, because this symmetry of conjugation would take n to minus n plus 1. So, on the one hand, on functions of x, operators that are made of functions of x, these symmetries comprise the group O2. On the other hand, when we have realized these symmetries on the ground state wave functions, if you're very quick with algebra in your head, you will see that U alpha times C is not the same as C times U alpha. In fact, if you do a small calculation, you'll find that U alpha C is not the same as C U minus alpha. They differ by a diagonal matrix, a scalar matrix, which I think is e to the minus I alpha. No, plus I alpha. So if you do a small calculation, you'll see that actually the group law of O2 is not obeyed. So what is the terminology? The terminology is that at phi equals 0, we have an O2 symmetry without an anomaly. But at phi equals pi, the O2 symmetry is anomalous. And that's why the ground state is twofold degenerate. Because the ground state is in a representation of the projective symmetry, of the projective Z2 times Z2 group, is in a projective representation of Z2 times Z2. Okay? Are there any questions about the... You could ask, is this necessary? Maybe I can remove this e to the alpha. You could say, maybe I can define some V alpha, which is e to the minus I alpha by 2 U alpha. And then you could say, oh, but for this V alpha C is the same as C, V minus alpha. So maybe this phase is actually spurious. The problem is that when you do that, then V is not going to be invariant under alpha going to alpha plus 2 pi. If you shift alpha by 2 pi now, V alpha picks a minus sign. So you'll have a projective phase whatever you do. There is a non-trivial projective phase in the realization of the symmetries on the ground state, whatever you do. Okay? And now I wanted to finish with some interesting consequence. Yes?
Well, I'm sure you're right, but I don't quite understand what you wrote, because if you change U alpha to V alpha, the conjugation on C won't change.
No, it will, because here it's minus alpha, you see? This is the O2 symmetry. So you'll get from
V
here.
alpha is just a constant times U alpha, right?
It's a constant matrix times U alpha.
So when you conjugate by V alpha,
yes,
it just cancels out, right?
No, but this is V alpha and this is V minus alpha.
Oh, I see. Okay.
It's the O2 symmetry.
Okay, yeah, good.
So it's a semi-direct product.
Yeah, thank you.
Is it a projective of O2 or is it enough? I mean, to do alpha equals pi? To get a Z2.
Excellent. So it's a projective O2. So in this simple model of a particle moving on a ring with pi flux, the classical symmetry of O2, but the quantum symmetry is bigger. It's O2 hat. O2 hat in mathematics is called pin2. So this is, if you just want to make a precise statement about this model, you could say that at a half flux, the classical symmetry is O2, but it's anomalous, and the correct symmetry is pin2. Okay? Now, it turns out that you don't actually need complete symmetry with respect to translations on the circle. And that's where the connection with Z2 times Z2 will come. So maybe that's what you're referring to. So that's what I wanted to say next. An interesting comment here is that we can note that it's enough that the ring, even if the ring is not homogeneous, let me just draw a non-homogeneous ring. Even if the ring is non-homogeneous, but it has a symmetry under translations by pi. So even if that even if the ring only has a symmetry where x goes to x plus pi, it's actually enough to have a non-trivial phase, because then we have u pi times c equals minus c times u pi. So the phase still survives even if the ring is not completely homogeneous. Okay? And that leads to an interesting consequence, because it means that even if we add some perturbations to this quantum system, as long as they're invariant under x goes to x plus pi and x goes to minus x, there will be some degeneracy in the ground state. So let's add cosine of 2x. Now this quantum system is not solvable anymore. Previously I solved the free particle model, so you could say, oh, who cares, it's completely boring. We knew the solution and we knew that it's twofold degenerate, even without talking about anomalies and spin groups. But the benefit of discussing it in the way I've discussed it is that it's very clear now that even if you make the ring non-homogeneous, let's say you had a potential like cosine 2x, the twofold degeneracy cannot go away. And just because there is this minus sign, so there is no way that the ground state wave function would be invariant under u pi and c. That will be inconsistent with the projective, with realizing z2 times z2 projectively. So therefore this qubit, or this twofold degeneracy, is extremely quantum mechanically robust, even if the system has non-trivial interactions. So classically, you would say it's a particle in a ring with some inhomogeneity. So there are two ground states, at x equals pi over 2, and x equals 3 pi over 2, where that's where the cosine function would be minimized. And then you would say, oh, in quantum mechanics, we learned that between minima there is tunneling, right? You learn in quantum mechanics that if there are two degenerate minima, there is a tunneling amplitude, and the full ground state is unique, it's non-degenerate. Here, I'm telling you something interesting. I'm telling you that there is a ground state here, there is a ground state here due to the cosine potential, but all the tunneling events exactly cancel out. So the tunneling events all cancel out, including multi-instantons, and the twofold degeneracy is exact because of an anomaly in the z2 times z2 symmetry. And that's probably the first example where you can see that the anomalies bias something. You keep hearing people talking about Hooft anomalies and their matching. So that's the simplest example where you have a model that's not solvable, and the anomaly implies that it has a twofold degeneracy, robustly. Yeah, there was a question. Okay, so what am I going to do next? So next, tomorrow we'll talk about extended operators which are non-topological. I'll tell you a little bit about renormalization group flows on non-topological extended operators. And then I'll discuss some interesting examples in simple quantum field theories and many-body systems. And what do we know about their solution? Yes, Frank?
If instead of the circle you take the line, it's well known that quantum mechanics is also transforming projected beyond the Galilei transformations. Is this any way related to this?
Which transformation?
The Galilei.
Yeah, I know about. Yeah, you can think about Galilean. So in the Galilean group, it's known in quantum mechanics, if you study the commutator of the Galilean boosts and translations, you get a mass on the right-hand side. And it's very interesting to interpret it as an anomaly, a Hooft anomaly for the Galilean symmetry. And it has far-reaching consequences if you interpret it as a Hooft anomaly and you try to match it in non-trivial quantum systems with Galilean symmetry. So the coolest application I know is you take a system of free electrons with interactions. They have Galilean symmetry. And then you assume that in the infrared they go to a Fermi surface. Just because of the strong interactions, whatever. They become a Fermi surface. Sometimes in the infrared, the effective mass changes to m star. Like in metals, the electrons have an effective different mass. But the fact that the anomaly has to be matched by the ground state implies that the electrons have some interactions, which are called Landau parameters. So you can derive the fact that in metals, when the effective mass of the electron is not equal to the bare mass of the electron must be interacting. And you can just derive it from anomaly matching. It's almost the same exercise as what I did. So yes, you can interpret the Galilean algebra as an anomaly, and it has far-reaching applications in cold gases and cold Fermi gases. Yes, that's a good comment. But that's an internal symmetry. Well, from the quantum mechanics point of view, it's a little more subtle than the Z2 times Z2 example. But it's very much the same conceptually. Yeah. Any other comments or questions about the quantum mechanics example or anything else? Yeah.
In this lambda cosine 2x, do you assume that is unit length your circle or something?
No, x like that. I assume that the circumference is 2 pi. I just took 2x so that it's invariant under x goes to x plus pi. That's why I drew the circle.
Okay, good.
That's why I drew the circle like that. It's as if somebody just deformed the circle and killed the.
So it has to have this symmetry, the potential.
Yeah. So what happens if you destroy the Z2 translational symmetry? Then you're only left with with C, and that's not enough to have a projective symmetry, because there is no projective representations for Z2. There are projective representations for Z2 times Z2, but there is no such thing as a projective representation of Z2. So you have to have at least Z2 times Z2 symmetry, or SL3. Another example that I plan to cover, but I ran out of time, is the Bloch sphere. The simple model of a Bloch sphere in quantum mechanics also has an anomaly for SL3 symmetry.
Monopoles?
Yes, the SL3 symmetry. I wanted to cover this story with the magnetic monopoles, but
next lecture, yes?
No, but I ran out of time. Yeah. So I wanted to give another example, which is a particle moving on a sphere with a magnetic monopole inside. That's another cool example of a quantum mechanical degeneracy that cannot be lifted by perturbations. But okay, this example is enough for now. Any other questions? Yeah.
Has this anomaly been observed experimentally?
Has this anomaly been observed experimentally? I actually spent quite a bit of time trying to understand that. So first of all, this qubit is very closely related to what quantum computer people call the superconducting qubit. It's almost the same equations. Have they really checked that when you deform it and you destroy the symmetries, you still get a full qubit? I don't think so. I'm not sure that it was experimentally verified.
Is it a mathematical fact that there's only two-dimensional projective representation?
Yeah, I mean, if you accept that these are, well, one is mathematical fact, another is experimental verification. I don't think Andy was asking if the mathematics is correct, right? He was asking if in a superconducting qubit people have seen this phenomenon. The mathematics is very simple. If you have a Z2 times Z2 symmetric classical system, but quantum mechanically there is an anomaly, and the anomaly is this minus sign, then there cannot be a single ground state. That's the mathematics.
Yeah, but can you have other, like, can it be triply degenerate?
It can be higher. It can be higher degenerate. Yes, it will probably be not very. It will be slightly fine-tuned, maybe.
But is it a mathematical question, sort of, what are the possible degeneracies?
Yeah, I mean, can I prove to you that for any non-zero lambda it's twofold degenerate? No, but it has to be at least twofold degenerate.
So can you rule out, say, it cannot be, I don't know, 5 degenerate?
Well, for infinite lambda, the classical approximation is correct. So there has to be two ground states. And then I just proved that instantons cannot lift the twofold degeneracy. So for large lambda, it's obvious. For lambda equals 0.1, I don't know. Yeah, it has to be put on the computer and checked. Yeah.
Is this actually your definition of an anomaly, that there is no way of making a unique symmetric ground state?
You could take it as a definition, but that's not the definition in the literature. If you look at, people have tried to understand how to define anomalies for generalized symmetries, non-invertible, blah, blah, blah. And actually one definition in one of the papers that I read was exactly what you said. It's a symmetry that cannot be trivially gapped. So we might need to adopt this definition in the future, because I don't think people have found a better definition. For invertible symmetries, there is a better definition, which is that the symmetries cannot be gauged, or that some defect Hilbert spaces are doubly degenerate, etc. But for generalized symmetries which are non-invertible, we might end up with your definition. Any last questions? Okay, thank you.
Thank you much.